Hi everyone, I'm Yi-Hao Peng. Today I'm going to present WalkingVibe, reducing virtual reality sickness and improving realism while walking in VR using unobtrusive hand-mounted vibrator feedback. This is the joint work with my advisor, Professor Neng-Hao at National Taiwan University of Science and Technology and Professor Mike Chen at National Taiwan University. I would also like to show my gratitude to my lab mates and collaborators across different universities. So walking in VR has been widely adopted in many daily applications, such as first-person shooting games, the VR touring systems, and 360-degree videos. However, those applications might not be accessible for everyone. Why? Well, there's one common barrier called VR sickness that keeps the user from enjoying the experiences. So VR sickness is a common symptom users face while navigating VR, which will cause people headaches or nausea, and thus they would tend to end up the experiences in a short period of time. Previous research has pointed out that the VR sickness and discomfort might be caused from a sensory mismatch between visual and vestibular system. Studies have also shown that 18 to 95% of VR users experience some of symptoms of sickness. So how could we tackle this well-known issue? Well, in fact, there are a couple of types of solutions that have been proposed. The first common type of solution is called visual modification, which reduces users' field of view and optic flow around users' periphery. Despite the effectiveness, studies have shown that this type of solution often degrades the sense of users' immersion during the experience. The second type of solution is called body movement, providing walking naturalness and thus mitigates sickness. This technique, however, will cause fatigue easily and limit the interactions between limbs and environment. The third type of solution is external stimulation, which applies visual vestibular recoupling approaches to employ physical stimulation around the vestibular system, which includes airflow, galvanic stimulation, and bone conductive vibration. These previous approaches still are either limited to certain type of application scenario, such as biking, or broad discomfort for users due to the selective level and type of stimulation. To provide better unobtrusive stimulation solution in last year IEEE VR, our team introduced Phantom Legs, the head-worn haptic devices that applies alternative taping cues that are synchronizing to users' footsteps in VR. As users navigate through a VR environment while physically being seated, our preliminary results show that Phantom Legs significantly reduce VR sickness while remaining comfortable to users. However, the noise generated from the servos of lab prototype were noticeable and had affected the VR walking experiences. In addition, the servo-based design contributed significant bulk and weight relative to the VR headset. Therefore, we ask ourselves if there is a more non-intrusive and easily integrated solution. In this work, we propose WalkingVibe, which applies unobtrusive Vibrotactile feedback using integrated, lightweight vibration motor system for VR walking experiences. This kind of design meets our initial goal on making feedback non-intrusive and can be easily integrated. To balance effectiveness with unobtrusiveness, we set the vibration frequencies to about 150 Hz that provide reasonable vestibular responses and lower perceived annoyance. Our initial idea is to provide vibrotactile feedback near user vestibular system and synchronize the feedback with users' virtual step. Then we found out there are more designs need to be explored for our ultimate goal: reduce VR sickness and improve realism for VR walking experience. To better explore possible designs, we include two factors: placement and synchronization, to form a total of 4 design combinations. For placement, we consider two-sided placement, which paired vibrators are placed near users' vestibular systems. and backside placement, which only one vibrator placed on the user's back of neck. For synchronization, we consider the alignment between vibrations and the user's virtual step. The user step are represented as head-bobbing visual effect in the VR environment, and we include both synchronized and random pattern in our designs. So here is the demonstration of two-sided synchronized vibration. Here is two-sided random vibration. Here is a synchronized backside vibration. And last one, random backside vibration. To fully evaluate how our vibrotactile feedback affects users' VR walking experience, we conducted the user study to compare our proposed designs with 4 baseline conditions that are made out of different visual, audio, and haptic feedback. The baseline conditions were visual only without head-bobbing pattern, which the users basically shift during walking experience. Visual only conditions, which the head-bobbing pattern is applied as user's virtual step. Audio conditions, which the step sounds are synchronized with visual head-bobbing pattern. And tapping conditions, which is the two-sided synchronized tapping feedback we propose in Phantom Legs project. In total, there are 8 study feedback compared in our study, with 4 baseline and 4 WalkingVibe design conditions. During the experiment, participants were seated statically and passively walk through the VR environment. The study's decision for using a passive walking approach stemmed from insights in the literature that approach could induce stronger rates of sickness. The passive control has also been widely used in many VR scenarios, including 360 videos and VR experiences at theme parks. We chose seated as a scenario is because many prior work studying on VR sickness chose such study settings. Due to the number of conditions we have, we chose between subject comparison on 8 total conditions along with 30 participants for each condition. During the study, participants were asked to walk through consecutive checkpoints in 9 minutes. There are 3 different scenes shown in the study: the city, the forest, and the sci-fi passage. 3 different walking speeds are applied in turn during the VR walking experience. For our study's measurement, we conducted 3 different questionnaires throughout the experiment. The first measurement was the discomfort score, which the users continuously reported their discomfort level every 20 seconds during the study. High score means higher discomfort they perceive. The second measurement was simulated sickness questionnaire, which was widely adopted by many VR sickness studies. We asked the user to fill out the questionnaire before and after the study to calculate the relative sickness scores. The last measurement was users' perceived working realism, which the users rated the similarity between their VR and physical walking experiences. We report the results for the 3 measurements as follows. For the perceived discomfort during the study, we found that two-sided synchronized vibration let users perceive significantly less discomfort compared to all other conditions. Besides that, two-sided tapping feedback has significantly lower discomfort than visual only without head-bobbing feedback. As for the reported relative sickness score, 3 tactile conditions, including tapping and two-sided vibration feedback, significantly reduced participants' VR sickness, compared with 2 visual only and audio conditions. In order to further analyze the effect of our proposed design factors from the vibrotactile feedback, including the placement and synchronization factors, we ran a mixed factor 2x2 ANOVA on the relative sickness score for the factors of visual tactile alignment and the tactile placement. Our results show that two-sided vibrotactile feedback received lower relative sickness score compared to backside simulation. while the synchronization between visual and tactile feedback didn't show any significant effect. Some comments were mentioned to be explanation for the effectiveness of our proposed technique. The haptic feedback on both sides can make me feel better because it is similar with what I experienced while walking in real life. It seemed like I was getting massage while walking using WalkingVibe, which felt really comfortable and thus reduced my sickness. Besides the results of discomfort and VR sickness, we also discovered that two-sided synchronized vibration and audio feedback provided significantly higher walking realism compared to all other tactile and visual only without head bobbing condition. Several feedback related to realism from the user aligned with our quantitative results we got. The vibrotactile feedback that matched with the visual bobbing gave me a sense of walking in the environment. The audio that the servo motors of Vanderlist made, it sounds like it was a robot walking instead of me. I think I could easily ignore the haptic feedback from backside vibration after getting used to it due to the regular stimuli that was received. Based on the qualitative and quantitative results, we recommended that WalkingVibe with a two-sided step-synchronized vibration design as the most effective technique, since such feedback improves users' VR walking experiences, not only in considerations of mitigating VR sickness and discomfort, but also in enhancing perceived realism. Despite the effectiveness we discovered, we should still address that there were still several study limitations in this work. Due to the large number of study conditions and the already large scale of our study, we didn't get to explore active versus passive control and seated versus standing conditions, as those would double and quadruple the study size. Furthermore, the between-subject study design also limited the opportunity for a direct comparison on each feedback for the same targeted sample. Lastly, the time that we gave to users for experiencing VR walking were still limited. A longitudinal experience study on how each feedback affected VR sickness and discomfort across hours or days remains a future task for exploration. So to conclude this talk, I would like to talk a little bit about our vision and future research direction. Last year, we presented Phantom Legs, a handheld haptic devices that synchronize tapping feedback with VR walking steps, and found that such feedback could effectively reduce users' VR sickness. This year, we extend the idea of using haptics to enhance VR walking experiences by applying unobtrusive vibrotactile feedback on head. We then discovered that two-sided synchronized vibration feedback not only reduce users' VR sickness and discomfort, but also improve the perceived walking realism. We envision similar feedback mechanism to better enhance other virtual experiences, such as VR driving or surfing games, and would like to explore the spectrum of haptics to further create more comfortable and realistic VR experiences. And that's the end of my talk. Thanks for listening. If you have further questions, please contact me via my personal email, and I'm happy to answer any kind of questions. Thank you.